Good morning, sir. Good morning, Professor Moses,
Yeah.
colleagues. My presentation today is on the topic of complex analysis. And the topic in complex analysis that I'll be discussing is the functions of a complex variable. Just as we can map real numbers to real numbers, we can also map complex numbers to complex numbers. But because complex numbers are 2D, in two dimensions, but from the real numbers point of view, they're in two dimensions. Complex functions have two real inputs and they have two real outputs. And you can use this information to make graphs of the complex functions, like when they're transforming, like if you get a transformation from a circle to a cardioid, which I'm going to show you just now. So connecting back to real numbers requires some multivariable reasoning, and moreover becomes interesting to consider the images of subsets from the plane that they are substituted into the complex functions. That's from the real plane to a complex plane. Now, the analysis from this transformation point of view is highly visual. The definition of a complex variable is a function of a complex variable is a rule that assigns to each number z in the domain and d in the complex numbers. Just like how you would use x and y to map real numbers, this is how you would map complex numbers. And this is if z is equals to x plus iy and w is equals to u plus iv, then f into x plus iy will be equals to f of z, and f of z will be equals to w. W is equals to u. Since w is equals to u plus iv, u plus iv itself would be equals to u into xy plus iv into xy. So every complex function could be considered as a pair of real functions, u and v, for two real variables. This is the first example. You want to map this function, so you find the real and the imaginary parts of 1 over z, and we get the real part, and we get the imaginary part with I. This is another example. Shucks. This is z squared, f of z equals to z squared. We get a real part, which is x squared minus y squared. We get the imaginary part, which is plus I into 2xy. Now when we want to visualize these functions, the function that I just showed you with z squared, when you map it onto a complex plane, you can see how it behaves. This is z squared, just dealing with the angles alone. We're dealing with the angles of the z squared. You can't feel me now. Oh, see this? You see it transfers from this angle and it moves to the left on the y-axis, through the y-axis. This is the z. This is the z square. And the regions of the z square. This is the transformation from the circle to a cardioid, right? And when you map this is the function down here. When you map it into a graphing calculator, if you don't put in the variables, you can see it transform like and transform from a circle into a cardioid. Yeah, it's supposed to. Yeah. Going, grows, and then just at the last minute, it starts to cut. Turns into a cardioid. Yeah. Now this is Z2 maps onto hyperbola of 2xy C2 as a second circle. This is the hyperbola mapping onto the second circle. Turns from a hyperbola into a line, y equal to x line, y equal to 1 line. In this example, we map the Z2 with a region in the first quadrant between the axis of the hyperbola Zx 2xy to the second circle. Same argument. This one here, you can get a line on the y-axis with the hyperbola. Both going to be moving downwards. So this is two functions in itself moving together, two complex functions. Two functions with complex variables. Now when you square root that same function, it just goes back up to the original position if you square root it. Move back to the original position. And that's how functions with complex variables work.